In early 1929, an astronomer named Edwin Hubble made an observation that would shatter humanity's understanding of the cosmos. Working at the Mount Wilson Observatory in California, Hubble had spent years meticulously measuring the light from distant galaxies, and what he found was shocking. These galaxies weren't stationary. They were moving away from us. More precisely, the further away a galaxy was, the faster it appeared to be receding. Space itself was expanding, carrying galaxies along with it like raisins in rising bread dough. This wasn't just a revolution in astronomy. It was a revolution in how we understand time itself. If the universe is expanding now, that means it was smaller in the past. Rewind far enough, and everything we can see, every galaxy, every star, every atom, was compressed into a smaller and smaller space. Keep rewinding, and you eventually arrive at a moment roughly 13.8 billion years ago when all of space, all of matter, all of energy existed in a region smaller than an atom. This is what we call the Big Bang. But here's the thing that keeps physicists awake at night. If the Big Bang was the beginning of everything, what started it? What caused the universe to suddenly explode into existence? This isn't just a casual question. It's arguably the most profound mystery in all of science. Because if you think about it for more than a few seconds, you quickly realize we're asking about something that shouldn't be possible to ask about. The Big Bang wasn't an explosion in space. It was an explosion of space. There was no location where it happened because location itself didn't exist yet. There was no before the Big Bang because time itself began at that moment. Asking what came before the Big Bang is like asking what's north of the North Pole. The question contains a logical paradox, and yet, here we are, asking it anyway. Because if there's one thing humans are extraordinarily good at, it's refusing to accept that some questions might be unanswerable. Let's start with what we actually know. In the early 20th century, most scientists believed the universe was eternal and unchanging. This idea, called the steady-state universe, seemed to make intuitive sense. Stars are born, stars die, but the overall structure of the cosmos remains constant. Einstein himself was so convinced of this eternal, static universe that when his own equations of general relativity predicted an expanding or contracting universe, he added a fudge factor, something he called the cosmological constant, to force the mathematics to describe a stable, unchanging cosmos. He would later call this the biggest blunder of his career. But, in fairness to Einstein, the idea that the universe had a beginning was deeply uncomfortable to many scientists. It felt too much like the old religious creation stories. Science was supposed to deal with natural processes, not divine acts of creation. An eternal universe avoided all those thorny, philosophical problems. Then Hubble ruined everything. His observations were undeniable. Galaxies were receding from us in all directions, and the relationship between their distance and velocity followed a precise mathematical pattern now known as Hubble's law. There was no way around it. The universe was expanding, and if it's expanding now, it must have been smaller in the past. A Belgian priest and physicist named Georges Lemaitre was one of the first to grasp the implications. In 1931, he proposed what he called the primeval atom hypothesis. The idea was simple but radical. If you run the expansion backward in time, you eventually reach a moment when all the matter and energy in the universe was concentrated in a single point. Lemaitre called it the primeval atom. Today, we call it the Big Bang, a name coined mockingly by astronomer Fred Hoyle, who never accepted the theory and spent his entire career trying to disprove it. The evidence for the Big Bang continued to mount throughout the 20th century. In 1964, two radio astronomers named Arno Penzias and Robert Wilson were testing a sensitive antenna in New Jersey when they detected a persistent background noise they couldn't explain. No matter where they pointed their antenna, no matter what time of day or night, the noise was always there. At first, they thought it might be interference from pigeon droppings that had accumulated in their equipment. They cleaned out the antenna, shooed away the pigeons, and tested again. The noise remained. What they had discovered, though they didn't know it at the time, was the cosmic microwave background radiation. This is the afterglow of the Big Bang itself, the cooled remnant of the intense heat that filled the universe in its first moments. When the universe was very young, it was so hot that atoms couldn't form. Any electrons that tried to bind to atomic nuclei were immediately knocked free by high-energy photons. The universe was opaque, a roiling soup of particles and radiation. But about 380,000 years after the Big Bang, the universe had expanded and cooled enough for atoms to form. Suddenly, photons could travel freely through space. The universe became transparent. Those photons have been traveling through space ever since, stretched by cosmic expansion from visible light into microwaves. When Penzias and Wilson detected that faint microwave glow coming from every direction, they were quite literally seeing the echo of creation. They won the Nobel Prize for their discovery. So, by the late 20th century, the Big Bang theory wasn't just accepted. It was the foundation of modern cosmology, supported by multiple independent lines of evidence. The expansion of space, the cosmic microwave background, the abundance of light elements like hydrogen and helium, all of it fit together into a coherent picture. The universe began in an incredibly hot, dense state, and has been expanding and cooling ever since. Case closed, right? Not even remotely, because the more physicists studied the Big Bang, the more problems they found. The first problem is the most obvious one. What we call the Big Bang theory actually describes what happened after the universe began, not the beginning itself. It tells us about the expansion and cooling, about how particles formed, and how those particles clumped together to eventually make stars and galaxies. But it says absolutely nothing about the moment of creation. It can't. At the very beginning, at what physicists call time equals zero, all the matter and energy in the universe was compressed into an infinitely small point called a singularity. And here's where physics completely breaks down. Singularities are places where the laws of physics as we understand them simply stop working. Density becomes infinite. Temperature becomes infinite. The curvature of space-time becomes infinite. When your equations start spitting out infinities, that's math's way of telling you that you've gone beyond the limits of your theory. General relativity, Einstein's theory of gravity that describes the large-scale structure of the universe, predicts this singularity. But general relativity also tells us not to trust anything it says about singularities. It's like a calculator displaying an error message. The theory is screaming at us that we need new physics to understand what actually happened at the moment of creation. Then there's what's called the horizon problem. When we look at the cosmic microwave background, we see that it's incredibly uniform. The temperature in one direction differs from the temperature in the opposite direction by only about 1 part in 100,000. This uniformity is puzzling because those two regions of space have never been in contact with each other. They're separated by such vast distances that light hasn't had time to travel between them in the entire history of the universe. So, how did they end up at exactly the same temperature? It's like finding that two strangers on opposite sides of the Earth are wearing identical custom-made outfits despite never having communicated. Something must have coordinated them. But what? The standard Big Bang model has no explanation for this. Next is the flatness problem. When cosmologists talk about the geometry of space, they mean something very specific. Space could be curved like the surface of a sphere, in which case parallel lines eventually converge. Or it could be curved like a saddle, where parallel lines diverge. Or it could be perfectly flat, where parallel lines stay parallel forever. Measurements of the cosmic microwave background tell us that our universe is extraordinarily close to perfectly flat. The curvature, if any, is less than 1%. Here's why that's strange. In the early universe, even tiny deviations from perfect flatness would have been amplified dramatically by expansion. If the universe was even slightly curved, in the beginning it should be obviously and dramatically curved today. The fact that it's still so close to flat after nearly 14 billion years of expansion means it must have been fine-tuned to an absurd degree in the beginning. We're talking about precision to something like 50 decimal places. Why would the universe start out so perfectly balanced? It's like balancing a pencil on its point and finding it still standing 50 years later. Technically possible, but it screams out for an explanation. There's also the monopole problem. Certain theories in particle physics predict that the extreme conditions of the early universe should have produced vast numbers of magnetic monopoles. These are hypothetical particles that have only a north pole or only a south pole, unlike ordinary magnets which always have both. If these theories are correct, the universe should be absolutely swarming with magnetic monopoles. They should be as common as protons. We should be tripping over them. But despite decades of searching, we've never detected a single one. Where did they all go? These problems, the singularity, the horizon problem, the flatness problem, the monopole problem, they all pointed to something missing in our understanding. The standard Big Bang model worked brilliantly for describing the universe from about 1 second after the beginning onward. But those first few moments remained a mystery. And it was in those first moments we increasingly realized where all the really important stuff happened. This is where we get into some deep philosophical territory. For most of human history, the question of how the universe began was considered a religious or philosophical question, not a scientific one. The book of Genesis describes God creating the heavens and the earth. Hindu cosmology speaks of endless cycles of creation and destruction. Many ancient Greeks believed the universe was eternal. These were matters of faith or philosophical speculation because they dealt with something that seemed forever beyond the reach of observation and experiment. But in the 20th century, cosmology became an experimental science. We could observe the cosmic microwave background. We could measure the expansion rate of the universe. We could calculate the abundance of elements produced in the Big Bang. Suddenly, questions about the origin of the universe weren't just philosophy. They were physics. This created an interesting tension. Many scientists were uncomfortable with the Big Bang specifically because it implied a moment of creation. The steady-state theory remained popular well into the 1960s, precisely because it avoided this problem. An eternal, unchanging universe doesn't require an explanation for how it began, because it never began. The discovery of the cosmic microwave background essentially killed the steady-state theory. but the discomfort remained. Even some scientists who accepted the Big Bang tried to avoid its implications. Maybe the universe underwent an infinite series of expansions and contractions, each Big Bang followed eventually by a big crunch that triggers the next cycle. Maybe our Big Bang was just one event in an eternally existing multiverse. The core issue is this. In physics, we're used to the idea that every effect has a cause. Billiard balls don't start moving unless something hits them. Particles don't decay unless they're unstable. The universe doesn't spontaneously develop new properties out of nowhere. This principle of causation is so fundamental to how we do science that we barely even think about it. But causation requires something very specific. It requires time. Cause comes before effect. That's what causation means. But if time itself began with the Big Bang, then the very concept of causation breaks down. There was no before the Big Bang during which something could have caused it to happen. This is why some philosophers argue that asking what caused the Big Bang is a category error. It's like asking what the smell of the color 7 is. The question mashes together concepts in a way that doesn't make logical sense. But physicists are stubborn. Instead of accepting that the question might be fundamentally unanswerable, they started looking for ways to make sense of it. Maybe time didn't begin with the Big Bang after all. Maybe the Big Bang was just a transition from some previous state. Maybe the laws of physics themselves allow for effects without causes under certain extreme conditions. Maybe we need to think about time differently. These aren't just abstract philosophical musings. They're questions that can potentially be answered with mathematics and tested with observations. And this is where things get really interesting. Because once you start digging into these questions, once you start taking seriously the challenge of explaining what could have started the Big Bang, you end up in some of the strangest territory in all of physics. You end up talking about universes tunneling into existence from nothing, about space and time being emergent properties rather than fundamental ones, about infinite numbers of parallel universes, about the possibility that the Big Bang wasn't the beginning at all, but just the latest in an endless series of cosmic bounces. The story of how physicists have grappled with the origin of the Big Bang is a story about the limits of human knowledge. It's about the question of whether some mysteries are forever beyond our reach, or whether given enough time and cleverness, we can understand anything. It's about the tension between our desperate desire to know where we came from and the humbling recognition that we might be asking questions that don't have answers, at least not in any conventional sense. 13.8 billion years ago, something happened. We don't know what. We don't know why. We're not even entirely sure those questions make sense. But we do know that whatever it was, it set in motion a chain of events that led, eventually, to stars and planets and life and consciousness and curious apes staring up at the night sky, trying to figure out where it all came from. We are, in a very literal sense, the universe trying to understand itself. And if that's not worth investigating, then nothing is. So, how do physicists approach this seemingly impossible question? What tools do we have for probing an event that happened before time began, if that phrase even means anything? The answer lies in following the evidence backward, working our way from what we can observe to what we can theoretically infer to what we can barely imagine. We start with Hubble's observations of galactic recession. We rewind the expansion. We trace the cosmic microwave background back to its source. We calculate what conditions must have been like in the early universe based on the particles and forces we can study in laboratories today. And we push that extrapolation back further and further, into the first minutes, the first seconds, the first fractions of a second after the Big Bang. The picture that emerges is both awe-inspiring and deeply puzzling. At 1 second after the Big Bang, the universe was about 10 billion degrees Kelvin, filled with a soup of neutrons, protons, electrons, photons, and neutrinos. Over the next few minutes, nuclear fusion began, creating the first atomic nuclei, mostly hydrogen and helium. This is called Big Bang nucleosynthesis, and we can calculate exactly how much of each element should have been produced based on the density and temperature of the universe at that time. When we look at the universe today, the abundances of these light elements match the theoretical predictions with stunning accuracy. This is one of the most powerful pieces of evidence for the Big Bang, but we can push back even further. At 1 millisecond after the Big Bang, the universe was hot enough that quarks hadn't yet combined into protons and neutrons. This was the quark-gluon plasma era, a state of matter so extreme that we can only recreate tiny samples of it for microseconds in particle accelerators. At 1 microsecond, even more exotic particles filled the universe, many of which we've only discovered in the last few decades. We can trace the history of the universe back to about 10 to the negative 12 seconds, a trillionth of a second after the Big Bang. At this point, the universe was about 1,000 trillion degrees, and our understanding of particle physics is good enough that we can make confident predictions about what was happening. Before that, we're in more speculative territory, but our theories of particle physics allow us to make educated guesses back to about 10 to the negative 36 seconds. And it's here, in these first incomprehensibly brief moments, that something extraordinary happened. Something that might hold the key to understanding not just what happened during the Big Bang, but what caused it. This is where Alan Guth enters our story. In 1979, Guth was a young physicist working on particle physics problems that seemed to have nothing to do with cosmology. He was thinking about magnetic monopoles, those hypothetical particles that should have been produced in vast numbers in the early universe, but that we've never detected. Guth realized that if the universe underwent a brief period of extraordinarily rapid expansion in its first moments, those monopoles would be diluted to the point of being undetectable. Any that were produced would be spread so far apart by this expansion that we'd never expect to find one. This rapid expansion became known as cosmic inflation, and Guth realized it solved not just the monopole problem, but all the other problems with the Big Bang theory. If the universe expanded by an enormous factor in an infinitesimally brief time, regions that were initially in close contact would be flung far apart, explaining why distant parts of the universe have the same temperature. The expansion would also flatten out any initial curvature, explaining why space appears so geometrically flat today. It was an elegant solution that seemed too good to be true. But here's the really crucial point. Inflation doesn't just explain what happened after the Big Bang. It provides a potential mechanism for what started it. And that's where we're headed next. Because once you understand inflation, once you grasp how quantum fields can make space itself expand at faster than light speeds, you start to see how something like the Big Bang might not need a traditional cause at all. You start to see how the universe might have created itself. Now, before we dive into that, we need to clear up a common misconception. When physicists talk about the Big Bang happening everywhere at once, people often imagine an explosion in empty space, like a bomb going off. That's completely wrong. The Big Bang didn't happen at a point in space. It happened at every point in space simultaneously because space itself was compressed to a point. Imagine you're standing on the surface of a balloon, and someone starts inflating it. Every point on the balloon's surface moves away from every other point. There's no center to the expansion on the balloon's surface. It's expanding everywhere at once. That's what the expansion of the universe is like, except in 3 dimensions instead of 2. The Big Bang happened here. It also happened 13 billion light-years away in that direction, and 13 billion light-years in the opposite direction. It happened everywhere because everywhere was once the same place. This is one reason why the question of what started the Big Bang is so tricky. We're not looking for a specific location where something happened. We're looking for an explanation for why space itself began expanding everywhere at once. And more fundamentally, we're looking for an explanation for why space, time, matter, and energy exist at all. This is where physics starts to blur into metaphysics. Metaphysics asks questions about the fundamental nature of reality. What does it mean for something to exist? Why is there something rather than nothing? These questions have traditionally been considered beyond the scope of science. Science tells us how things work, not why they exist in the first place. But modern physics has started to encroach on this territory, and it's doing so by challenging some of our most basic assumptions about concepts like nothing and something, cause and effect, existence and non-existence. Take the concept of nothing, for example. In everyday language, nothing means the absence of anything. Empty space, a void. But in physics, empty space is far from nothing. According to quantum mechanics, the theory that describes the behavior of particles at the smallest scales, empty space is teeming with activity. Virtual particles constantly pop in and out of existence, borrowing energy from the vacuum for a brief instance before annihilating each other. Quantum fields pervade all of space, even where there are no particles. These aren't just theoretical ideas. We can measure the effects of these quantum fluctuations. The Casimir effect, for instance, demonstrates that 2 metal plates placed very close together in a vacuum experience a force pushing them together. This force arises from quantum fluctuations in the electromagnetic field being slightly suppressed between the plates compared to outside them. So, when physicists talk about the universe potentially arising from nothing, they don't mean absolute philosophical nothingness. They mean a quantum vacuum, a state with no particles, but with quantum fields, and the potential for fluctuations. This might seem like cheating. If you start with quantum fields, you're not starting with nothing. You're starting with something, and that something obeys certain laws of physics. So, haven't we just pushed the mystery back a step? Where did the quantum fields come from? Where did the laws of physics come from? This is a fair criticism, and it's one that philosophers are quick to point out. But the physics here is genuinely trying to address something profound. It's asking whether the laws of physics themselves might be sufficient to explain the existence of the universe without needing anything external. Whether the universe might be, in some sense, self-creating. There's a famous debate about this between physicists and philosophers. The physicists, led by people like Lawrence Krauss, argue that quantum mechanics shows how a universe can arise from nothing. The philosophers, led by people like David Albert, argue that the physicists are redefining nothing in a way that makes their achievement less impressive. If your nothing already contains quantum fields and laws of physics, then you haven't explained where those came from. Both sides have valid points. The physicists are genuinely explaining how you can get something from what they consider nothing. The philosophers are genuinely pointing out that this nothing isn't absolute nothingness. But here's the thing. Absolute nothingness might not be a coherent concept. It might not be possible, even in principle, to have a state with no properties whatsoever, no potential for change, no laws governing what can happen. Because if nothing has no properties and can't change, how can it transition into something? Absolute nothingness, if it were possible, would be absolutely static. Nothing could ever happen. Nothing could ever change. Nothing could ever begin. So maybe the fact that something exists tells us that absolute nothingness is impossible. Maybe existence is the default state, and it's nothingness that requires explanation. These are deep waters, and we're going to need to dive much deeper to really understand what modern physics says about the origin of the universe. But before we do, it's worth pausing to appreciate how far we've come. A century ago, the question of where the universe came from was pure speculation. There was no evidence, no mathematical framework for thinking about it rigorously. Today, we have detailed observations of the cosmic microwave background showing us what the universe looked like 380,000 years after the Big Bang. We have particle accelerators that recreate conditions from microseconds after the Big Bang. We have mathematical models that let us extrapolate back to the Planck time, 10 to the negative 43 seconds, the smallest meaningful unit of time in physics. We've pushed our understanding back to a point where the universe was smaller than a proton and hotter than anything we can imagine. We've identified specific problems with our models and developed potential solutions. We've made testable predictions and confirmed many of them with observations. But the ultimate question remains. What started it all? What lit the fuse? What caused the Big Bang to bang? As we'll see, there are several competing theories, each strange in its own way. There's cosmic inflation, which suggests that a special quantum field drove exponential expansion in the first fraction of a second. There's the idea that the universe tunneled into existence through a quantum fluctuation appearing out of the vacuum with a certain probability. There are cyclic models where our Big Bang was actually a big bounce, the latest in an eternal series of expansions and contractions. There are theories involving collisions between higher dimensional membranes, where our entire universe is just one three-dimensional slice of a much larger reality. Each of these theories is backed by serious mathematics and, in some cases, by experimental evidence. Each pushes our understanding of physics to its absolute limits, and each forces us to rethink our basic assumptions about time, causation, and existence itself. The question of what started the Big Bang isn't just a question about cosmology, it's a question about the nature of reality itself. And the answers, as we're about to discover, are far stranger than anyone could have imagined. In December of 1979, a young physicist named Alan Guth was lying in bed, unable to sleep. He had been working on a problem in particle physics for weeks, trying to understand why we hadn't detected magnetic monopoles despite theories predicting they should be everywhere. Around midnight, he suddenly realized the solution. If the universe had undergone a brief period of exponential expansion in its earliest moments, any monopoles that formed would have been spread so far apart that finding one would be like searching for a specific atom in the observable universe. Guth later wrote in his notebook that this was a spectacular realization. He drew a box around his calculations and added the words "spectacular realization" in capital letters. He wasn't exaggerating. What Guth had stumbled upon was nothing less than a revolution in cosmology. His idea, which came to be called cosmic inflation, didn't just solve the monopole problem. It solved essentially every major problem with the Big Bang theory in one elegant stroke. More importantly, for our story, it provided the first scientifically rigorous mechanism for what might have triggered the Big Bang itself. To understand inflation, we need to understand what it actually means for space to expand. This is something people often get confused about because the word expansion suggests things moving apart through space, like fragments from an explosion. But that's not what's happening. Space itself is expanding. The distance between any 2 points in space is increasing over time, not because those points are moving through space, but because new space is being created between them. Imagine you have a ruler made of rubber. Normally, the distance between the 1 centimeter mark and the 2 centimeter mark is, obviously, 1 centimeter. But if you stretch the ruler, that distance increases. The marks themselves haven't moved along the ruler. The ruler itself has expanded. That's what's happening with the universe. Galaxies aren't flying away from each other through space. Space is expanding, carrying the galaxies along with it. Now, in the standard Big Bang model, this expansion happens at a fairly steady rate. The universe expands and cools gradually over billions of years. But Guth realized that in the very early universe, something very different could have happened. For a brief moment, the expansion could have been exponential. Not gradual, but explosively fast. The universe could have doubled in size, then doubled again, then doubled again, over and over, in the tiniest fraction of a second. How fast are we talking? During the inflationary period, which lasted somewhere between 10 to the negative 36 and 10 to the negative 32 seconds, the universe expanded by a factor of at least 10 to the 26. That's a 1, followed by 26 zeros. To put this in perspective, imagine you have a grain of sand. Now expand it to the size of the observable universe. That's roughly equivalent to what inflation did to the universe. A region smaller than a proton expanded to something roughly the size of a grapefruit, or maybe larger, all in less time than it takes light to cross the diameter of a proton. This sounds absurd. It sounds like it violates the cosmic speed limit. After all, isn't faster than light travel supposed to be impossible according to Einstein's theory of relativity? And that's true. Nothing can move through space faster than light. But space itself has no such restriction. Space can expand at any rate whatsoever. There's no cosmic speed limit on the expansion of space itself. During inflation, galaxies or any objects that existed would not have been moving faster than light through space. Space was expanding so fast that the distance between any 2 points grew faster than light could travel between them. It's a subtle but crucial distinction. So, what caused this incredible expansion? The answer lies in a concept called the inflaton field. Now, in physics, a field is just a quantity that has a value at every point in space. Temperature is a field. You can measure the temperature here, over there, everywhere, and each location has a specific temperature value. The electromagnetic field is another example. It determines the strength and direction of electromagnetic forces at every point in space. Quantum field theory tells us that all particles are actually excitations or ripples in their corresponding fields. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. The inflaton field is a hypothetical quantum field that, if it exists, permeated all of space in the very early universe. What makes this field special is its potential energy. Most quantum fields have their lowest energy state at a value of 0. The inflaton field, however, had a peculiar property. Its lowest energy state was not at zero. Instead, the field could get stuck at a higher energy value, what physicists call a false vacuum state. Think of it like a ball sitting on a shelf protruding from a wall. The ball isn't at the lowest possible position. The floor below is lower, but it's in a locally stable position on the shelf. That's what the inflatoned field was doing. It was stuck at a high energy value, not because that was its ultimate lowest energy state, but because it was temporarily trapped there. Here's where things get interesting. When a quantum field has a high energy value everywhere in space, that energy creates a kind of pressure. But unlike normal pressure, which pushes outward, the pressure from a quantum field in a false vacuum state is negative. Negative pressure sounds weird, and it is weird. It's like a tension or a suction. And, according to Einstein's equations of general relativity, negative pressure has a bizarre effect. It causes space to expand. Not just expand, but expand exponentially. The more space you have, the more total energy there is in the inflaton field, and the faster the expansion becomes. It's a runaway process. Space expands, which creates more space, which contains more field energy, which drives even faster expansion, which creates even more space, and so on. This is cosmic inflation, a period where the inflaton field's potential energy drove exponential expansion of space. Now, this couldn't last forever. Eventually, the inflaton field had to roll down to its true lowest energy state, like the ball finally rolling off the shelf and settling on the floor. When that happened, all the potential energy stored in the inflaton field was converted into particles and radiation. This process, called reheating, flooded the universe with matter and energy. And this moment, this transition from the inflationary period to the hot, dense particle soup of the early universe, this is what we call the Big Bang. This is crucial, so let me say it again. In the inflationary picture, the Big Bang wasn't the beginning. It was the end of inflation. The hot, dense, expanding universe that we traditionally think of as emerging from the Big Bang was actually the result of the inflaton field decaying and converting its energy into normal matter and radiation. The actual beginning, if there was one, was whatever started the inflaton field rolling in the first place. But before we get to that question, let's talk about why inflation was such a spectacular realization. Remember the horizon problem. The puzzle of why distant regions of the universe have the same temperature even though they've never been in contact. Inflation solves it beautifully. Before inflation, the entire observable universe was compressed into a tiny region, much smaller than the size of an atom. At that scale, everything was in thermal contact. Different parts of this tiny region could exchange heat and reach the same temperature. Then inflation happened. This tiny, uniform region expanded by a factor of 10 to the 26 or more. Regions that were once close neighbors were suddenly separated by vast distances. But they retained the same temperature because they started out in equilibrium before inflation separated them. When we look at the cosmic microwave background today and see that distant regions have nearly identical temperatures, we're seeing the memory of that pre-inflationary equilibrium. What about the flatness problem? Remember, the universe is remarkably close to being geometrically flat, so close that it must have been fine-tuned to absurd precision in the early universe, unless something flattened it out. Inflation explains this too. When you expand something by a factor of 10 to the 26, any curvature gets stretched out. Think about standing on the surface of the Earth. The ground beneath your feet looks flat even though you're standing on a sphere. That's because the Earth is so large compared to your size that the curvature is negligible at small scales. Inflation did the same thing to the universe. Any initial curvature that existed was stretched to such an enormous scale that our observable universe appears flat, even if the universe as a whole might still be curved. We're like tiny creatures standing on a small patch of an enormous balloon. The patch looks flat to us because we can't see enough of the balloon to notice its curvature. And the monopole problem. Inflation solves that too. If magnetic monopoles formed before inflation, they were diluted to incredibly low densities by the expansion. The observable universe might contain 0 monopoles, or maybe 1, or maybe a few scattered across scales larger than we can see. Either way, we wouldn't expect to detect any. It's like if you had a bag containing 100 marbles and you inflated that bag to the size of the observable universe. The chance of finding even 1 marble in the region we can see would be essentially 0. But inflation does more than solve the Big Bang's problems. It makes predictions. Very specific, testable predictions. And this is what separates inflation from mere speculation. One of the most important predictions involves quantum fluctuations. Remember, at quantum scales, nothing is perfectly uniform. Everything fluctuates randomly because of Heisenberg's uncertainty principle. Even the inflaton field, as it drove cosmic expansion, had tiny quantum fluctuations. Different regions of space had slightly different values of the field energy, varying by incredibly tiny amounts, something like 1 part in 100,000. Now, here's the beautiful part. When inflation ended and the inflaton field decayed into particles and radiation, those tiny quantum fluctuations became density variations in the resulting matter. Some regions ended up with slightly more matter, others with slightly less. And these density variations are exactly what we see in the cosmic microwave background. The temperature variations we observe, those subtle differences of 1 part in 100,000, match precisely what inflation predicts from quantum fluctuations in the inflaton field. But it doesn't stop there. Those same density variations became the seeds for all structure in the universe. Regions with slightly more matter had slightly stronger gravity, which attracted even more matter, which increased the gravity further, in a runaway process called gravitational instability. Over hundreds of millions of years, these tiny quantum fluctuations in the inflaton field grew into galaxies, galaxy clusters, and the vast cosmic web of structure we see today. Everything we see, every star, every planet, every atom in your body, owes its existence to quantum fluctuations during the inflationary epoch. This is genuinely one of the most profound ideas in all of science. The largest structures in the universe, superclusters of galaxies spanning hundreds of millions of light years, originated from quantum fluctuations smaller than a proton. The bridge between the quantum and cosmic scales is inflation. We can test this prediction. The cosmic microwave background should show a very specific pattern of temperature variations if they came from quantum fluctuations during inflation. The variations should be roughly the same strength at all scales, what's called a nearly scale-invariant spectrum. And when we measure the cosmic microwave background with satellites like COBE, WMAP, and Planck, that's exactly what we find. The data matches inflation's predictions with stunning precision. This isn't proof that inflation happened. Scientific theories are never proven, only supported or contradicted by evidence. But it's powerful support. Another prediction involves gravitational waves. Inflation didn't just produce density fluctuations in matter, it should have also produced fluctuations in space-time itself, gravitational waves that rippled through the universe during the inflationary epoch. These primordial gravitational waves would have left a subtle imprint on the cosmic microwave background, a specific pattern of polarization called B modes. Detecting this signal is extraordinarily difficult, and so far, we haven't definitively seen it. But experiments are getting more sensitive every year, and many physicists believe we'll detect primordial gravitational waves in the coming decades if inflation is correct. So, inflation solves the Big Bang's problems, makes testable predictions, and has been confirmed in several ways. It's become the standard model of the very early universe. Most cosmologists accept that something like inflation probably happened. But, and this is a big but, inflation doesn't actually solve the ultimate mystery. It pushes it back a step. If inflation explains what happened in the first fraction of a second after the universe began, what started inflation? What caused the inflaton field to start rolling? Where did the inflaton field come from in the first place? And this is where things get really strange. One of the most surprising features of inflation is that it never completely stops. Remember, inflation is driven by the inflaton field being stuck in a false vacuum state. Eventually, the field rolls down to its true lowest energy state, and inflation ends in that region. But at quantum scales, the inflaton field doesn't have a single definite value. It fluctuates, and in some regions, purely by chance, those fluctuations push the field back up toward the false vacuum state, causing inflation to continue in those regions even as it ends elsewhere. This leads to something called eternal inflation. Once inflation starts, it creates an infinite amount of space at an exponential rate. Even though inflation ends in some regions, converting the inflaton field's energy into matter and radiation to create a hot Big Bang, there are always other regions where quantum fluctuations cause inflation to continue, and those regions themselves spawn more regions where inflation continues. The result is an infinite fractal structure. Universes within universes within universes, each separated from the others by regions of eternally inflating space. Our Big Bang, in this picture, wasn't the beginning of everything. It was just one of countless bubbles nucleating within a vastly larger, eternally inflating space-time. Each bubble is its own universe with its own Big Bang, its own laws of physics potentially, its own galaxies and stars and planets. The multiverse isn't just speculation or science fiction in the inflationary paradigm. It's an almost unavoidable consequence of how inflation works. If inflation happened at all, eternal inflation is extremely difficult to avoid. And if eternal inflation is real, then the multiverse is real. Our universe, everything we can see with our most powerful telescopes, is just one bubble in an infinite foam of universes. Now, you might be wondering, doesn't this just make the problem worse? If we're asking what started our Big Bang, and the answer is inflation, and inflation is eternal and produces infinite universes, haven't we just created an even bigger mystery? Where did eternal inflation come from? And the answer is, yes, we have. But we've also gained something important. We've transformed the question from, why did the Big Bang happen, to, why did inflation start? And the latter question turns out to be much more tractable because quantum mechanics gives us a potential answer. In quantum mechanics, things don't need a cause in the traditional sense. Particles can spontaneously appear and disappear. Electrons can tunnel through barriers they classically shouldn't be able to cross. Radioactive atoms decay at random without any triggering event. Quantum mechanics is fundamentally probabilistic. Things happen with certain probabilities, but there's no deeper cause, no hidden mechanism determining exactly when or where. It just happens. And if quantum mechanics applies to the universe itself, then perhaps inflation didn't need a cause either. Perhaps it just happened, a quantum fluctuation in the primordial vacuum that set the inflaton field rolling. This is where we enter territory that sounds more like philosophy than physics, but it's actually based on rigorous mathematical models. In 1982, Alexander Vilenkin proposed that the universe could have tunneled into existence from nothing via a quantum fluctuation. The idea is based on quantum tunneling, a well-established phenomenon in quantum mechanics. Normally, a particle trapped in a valley by a hill can't escape unless it has enough energy to climb over the hill. But in quantum mechanics, there's a small probability that the particle can simply appear on the other side of the hill without ever crossing it. It tunnels through. Vilenkin applied this concept to the universe itself. If the universe in its inflationary state has lower energy, then absolute nothingness, whatever that means, then there's a quantum probability for the universe to tunnel into existence from nothing. No cause, no trigger, just a random quantum event with a certain probability. The universe, in this picture, is the ultimate quantum fluctuation. Now, this raises immediate questions. How can something have lower energy than nothing? Doesn't nothing mean zero energy? Not necessarily. In general relativity, gravitational energy is negative. The positive energy of matter and the negative energy of gravity can balance out, making the total energy of the universe zero or even negative. So, a universe in an inflationary state, dominated by the negative pressure of the inflaton field and with negative gravitational energy, could indeed have lower total energy than a state with no universe at all. Does this mean the universe created itself from nothing? In a sense, yes, but we need to be careful about what nothing means here. We're not talking about absolute philosophical nothingness. We're talking about a quantum vacuum, a state with no particles and no space but still governed by the laws of quantum mechanics. The quantum vacuum has properties. It has quantum fields. It has the potential for fluctuations. Is this really nothing? Philosophers would say no, and they have a point. But from a physics perspective, it's the closest thing to nothing that makes sense to talk about. Absolute nothingness, a state with no properties whatsoever, no laws, no potential for change, is probably not a coherent concept. If nothing has no properties, it can't do anything, including turn into something. So perhaps the right way to think about this is that the universe arose from the simplest possible state that can meaningfully be called a state at all, a quantum vacuum governed by the laws of quantum mechanics. And the question then becomes, where did those laws come from? This is the point where physics really does hit a wall. We can potentially explain how the universe arose from a quantum vacuum. We can potentially explain how inflation started from a quantum fluctuation. We can potentially explain how the Big Bang resulted from the end of inflation. But explaining where the laws of physics themselves came from, that might be forever beyond our reach. Or maybe not. Some physicists have speculated that the laws of physics could be emergent rather than fundamental. That what we call laws might just be patterns that arise naturally in any sufficiently complex system. Others have suggested that all logically consistent mathematical structures exist in some sense, and we happen to live in one that permits observers like us. This is known as the mathematical universe hypothesis, championed by cosmologist Max Tegmark. Still, others argue that the laws of physics might vary from universe to universe in the multiverse, and we observe the laws we do because only universes with these particular laws can produce observers to notice them. This is an application of the anthropic principle, which we'll come back to later. But let's return to inflation and what it tells us about the Big Bang. The key insight is that inflation transforms the Big Bang from a singular unexplained event into a phase transition, a change in the state of the inflatoned field. Phase transitions are common in physics. Water freezing into ice is a phase transition. A magnet losing its magnetism when heated is a phase transition. These transitions happen according to well-understood physical laws. They don't require mysterious causes, they just happen when conditions are right. If the Big Bang was a phase transition at the end of inflation, then it's not fundamentally mysterious. It's just physics. The mystery shifts to what started inflation, and as we've seen, quantum mechanics might provide an answer there. But here's where things get even more interesting. Different regions of the eternally inflating spacetime might undergo the phase transition from inflation to a hot Big Bang state at different times and in different ways. The properties of the resulting universes could vary. The masses of particles, the strengths of forces, even the number of dimensions of space could differ from one bubble universe to another. This is because, in many models of inflation, the inflaton field isn't the only quantum field involved. There could be dozens or hundreds of quantum fields, each settling into different values as inflation ends, and those values determine the properties of the resulting universe. It's like a ball rolling down a landscape with many valleys. Which valley the ball ends up in determines what kind of universe you get. Some valleys might produce universes with weak gravity and no atoms. Others might produce universes where stars can't form. Still, others might produce universes like ours where conditions are just right for complexity and life. If this is correct, and it's a big if, then our universe's properties aren't unique or specially designed. They're just one outcome among infinite possibilities. We find ourselves in a universe with these particular properties because only universes with properties like these can produce observers like us. Universes with different properties either don't last long enough, don't produce complex structures, or don't permit the chemistry needed for life. This is called the anthropic explanation for the universe's properties, and it's deeply controversial. Some physicists love it because it explains why so many fundamental constants seem fine-tuned for life without requiring a designer. Others hate it because it seems to give up on finding deeper explanations. If you can explain any observation by saying, "It has to be this way," or "we wouldn't be here to observe it," then what's to stop you from invoking that explanation for everything? It feels like intellectual surrender. The debate over the anthropic principle is fierce and ongoing. But regardless of how you feel about it, inflation has transformed our understanding of the Big Bang. We've gone from thinking of the Big Bang as the ultimate beginning of everything to seeing it as possibly just one event in a much larger structure. Our universe, vast as it is, might be a tiny bubble in an infinite foam. And that foam itself might have emerged from a quantum fluctuation in a primordial vacuum. It's dizzying to think about. But it's also, in a strange way, reassuring. Because it means the Big Bang, terrifying and mysterious as it seemed, might not be fundamentally different from other processes in physics. It might just be an extreme example of phenomena we already understand: quantum fluctuations, phase transitions, field dynamics. The universe might not require anything supernatural or incomprehensible, just quantum mechanics and gravity, taken to their logical extremes. Of course, we're not done. Inflation is our best current theory for the very early universe, but it's not the only theory. And it has problems of its own. For one thing, we don't know what the inflaton field actually is. We've never detected it directly. We've inferred its existence from its effects, but that's not the same as confirming it exists. It could be a new type of field we've never encountered before, or it could be some combination of fields we already know about. We simply don't know. There's also the measure problem in eternal inflation. If inflation produces infinite universes with all possible properties, how do we calculate the probability of anything? Normally, probability means counting outcomes. But when you have infinite outcomes of every type, counting doesn't work. Some physicists think this is a fatal flaw in eternal inflation. Others think it's a technical problem that will eventually be solved. Then there's the question of whether inflation is even testable in the way we usually think of scientific theories being testable. If the multiverse is real, but we can never observe other universes, can we really say the theory is scientific? Or has it crossed over into metaphysics? These are legitimate concerns, and they keep theorists up at night. But here's what we can say with confidence. Inflation, or something very much like it, almost certainly happened. The evidence from the cosmic microwave background is too compelling to ignore. The universe really did undergo a period of exponential expansion in its first moments. And that expansion really did smooth out the universe, flatten space, and generate the density fluctuations that became galaxies. Whether inflation was eternal, whether it produced a multiverse, whether it started from a quantum fluctuation, those are still open questions. But the basic idea that inflation occurred is now part of the standard cosmological model. And that means we've made real progress on understanding what started the Big Bang. It wasn't a mysterious singular event. It was the end of inflation, the moment when the inflaton field decayed and released its energy. The Big Bang was the universe's grand finale for the inflationary epoch, the spectacular conclusion of an exponential expansion that set the stage for everything that followed. But the story doesn't end there because we still haven't fully explained what started inflation, and there are alternative theories that challenge the entire inflationary picture. Some physicists think the Big Bang wasn't the end of inflation at all, but the result of a previous universe collapsing. Others think the universe has no beginning, that it's been cycling through expansions and contractions forever. And still others think the Big Bang happened when higher dimensional membranes collided in ways we can barely imagine. These alternative theories are where we're headed next, and they're going to take us even further down the rabbit hole. In the 1950s, a group of physicists began to seriously consider a disturbing question. What if the Big Bang wasn't actually the beginning? What if the universe has been around forever, cycling through endless repetitions of expansion and contraction, birth and death? Big Bang followed by Big Crunch followed by another Big Bang. The idea seemed almost absurd at first, but the mathematics worked. Einstein's equations of general relativity allowed for a universe that expands, slows down, eventually stops, and then collapses back in on itself. The collapse would end in another singularity, another point of infinite density, and perhaps that singularity could somehow bounce, triggering a new expansion. A new Big Bang. The cyclic universe model, as it came to be called, was attractive for several reasons. Most obviously, it eliminated the need to explain where the universe came from. if the universe has always existed, cycling forever through expansions and contractions, then there's no moment of creation to explain. No first cause to puzzle over. The question of what started the Big Bang becomes meaningless, because there never was a first Big Bang. Our Big Bang was just the latest in an infinite series. But the cyclic model faced serious problems. The most fundamental one is entropy. The second law of thermodynamics tells us that entropy, roughly speaking the amount of disorder in a system, always increases over time. You can't unscramble an egg. You can't unburn a piece of paper. Heat flows from hot to cold, never the reverse. And this applies to the entire universe. Each time the universe goes through a cycle, entropy increases. The universe becomes more disordered. But if the universe has been cycling forever, through an infinite number of cycles, then entropy should already be infinite. The universe should have reached maximum entropy long ago, a state called heat death, where nothing interesting can happen anymore because all energy has been evenly distributed, and there are no differences in temperature or density to drive any processes. The fact that we don't live in a maximum entropy universe suggests that either the cyclic model is wrong, or the universe hasn't been cycling forever, or there's some mechanism that resets entropy at the start of each cycle. For decades, this entropy problem seemed fatal to the cyclic model. But in the 1990s and 2000s, physicists Paul Steinhardt and Neil Turok developed a new version of the cyclic model that tried to address these issues. Their model, based on ideas from string theory, proposed that each cycle lasts not billions of years, but trillions. Our current universe is about 14 billion years old, but in the Steinhardt-Turok model, it will continue expanding for trillions of years more before the cycle repeats. And, crucially, they proposed a mechanism for how the bounce happens, how the universe transitions from contraction to expansion without ever reaching a singularity of infinite density. The key is something called the ekpyrotic scenario. The word ekpyrotic comes from ancient Stoic philosophy, referring to the periodic destruction and recreation of the universe by fire. In the Steinhardt-Turok model, our universe isn't alone. It's a three-dimensional membrane, or brane for short, floating in a higher dimensional space. There's another brane parallel to ours, separated by a tiny gap in this extra dimension. These branes are attracted to each other, and eventually they collide. When two branes collide, enormous amounts of energy are released. This energy heats up the branes, creating matter and radiation. From the perspective of beings living on one of the branes, this would look exactly like a Big Bang. The universe suddenly becomes filled with hot, dense particles. Space begins expanding. Stars eventually form. Galaxies appear. All the usual Big Bang stuff happens. But from a higher dimensional perspective, it wasn't a bang. It was a collision. Now, here's where it gets interesting. After the collision, the branes bounce apart. They move away from each other through the extra dimension, and as they separate, our three-dimensional universe expands and cools. Galaxies form, stars ignite, planets coalesce, life emerges, civilizations rise and fall. But all the while, the branes are still moving apart, though they are slowing down due to the attractive force between them. Eventually, they stop moving apart and start falling back together. The universe enters a phase of contraction. But this contraction doesn't mean galaxies are getting closer together, at least not at first. The contraction happens in the extra dimension, the dimension we can't perceive. Only in the very late stages of the contraction does our three-dimensional space itself begin to shrink. And then the branes collide again. Another burst of energy, another Big Bang, another cycle begins. The brilliant thing about this model is that it never requires a singularity. The branes never actually touch at a single point. They collide across their entire extent simultaneously. The density and temperature get very high during the collision, but not infinite. General relativity doesn't break down. We don't have to invoke quantum gravity or other speculative physics to understand what happens. It's just branes colliding, which is something that string theory, if correct, allows and predicts. But does the ekpyrotic model solve the entropy problem? Steinhardt and Turok argue that it does, or at least might. In their model, each cycle lasts so long, trillions upon trillions of years, that the universe has plenty of time to approach maximum entropy before the next collision. And when the collision happens, it generates new structure, new gradients of density and temperature, effectively resetting the entropy clock. The universe starts fresh with lots of low-entropy structure that can then decay over the next trillion years. Whether this actually works mathematically is hotly debated. Some physicists argue that you can't truly reset entropy, that information from previous cycles must carry over in some form, and that the entropy problem remains unsolved. Others think the mechanism works but requires very specific and perhaps unlikely conditions. The ekpyrotic scenario is elegant, but it's also speculative. String theory, which provides the theoretical framework for talking about branes and extra dimensions, remains unproven. We have no experimental evidence for extra dimensions. We have no evidence for other branes. We can't observe the collisions directly. The model makes some predictions about the cosmic microwave background that differ slightly from inflation's predictions. But so far, the data isn't precise enough to definitively rule one model in or out. So, the ekpyrotic model remains an intriguing alternative to inflation, but not a proven theory. There's another approach to avoiding the Big Bang singularity that comes from a completely different direction. This is loop quantum gravity, an attempt to reconcile general relativity with quantum mechanics by quantizing spacetime itself. In standard general relativity, space and time are smooth and continuous. You can divide space into smaller and smaller regions without limit. But loop quantum gravity suggests that at the tiniest scales, somewhere around the Planck length of 10 to the negative 35 meters, space itself becomes grainy or pixelated. Space, in this view, is made of discrete loops of gravitational field lines. You can't divide space into regions smaller than a Planck length any more than you can have half a pixel on a computer screen. This quantization of space has profound implications for the Big Bang. In classical general relativity, if you run the expansion backward in time, you eventually reach a singularity where density and curvature become infinite. But in loop quantum gravity, there's a natural limit to how much you can compress space. When you try to squeeze space down to the Planck scale, quantum effects become dominant, and something interesting happens. Instead of allowing infinite compression, the equations of loop quantum gravity predict a repulsive force, a kind of quantum bounce. The universe can compress to extremely high density, far higher than anything we can create in laboratories, but not infinite density. And then, before reaching a true singularity, the quantum nature of spacetime causes a bounce. The contraction reverses into an expansion. The big crunch becomes a Big Bang. This is an incredibly appealing idea because it elegantly sidesteps the singularity problem. There never was a moment of infinite density where physics breaks down. Instead, there was a moment of maximum density, enormous but finite, followed by a bounce. If loop quantum cosmology is correct, our Big Bang was actually a big bounce, the transition from a previous contracting universe to our current expanding one. What was the previous universe like? According to the simplest versions of the theory, it was very similar to ours. Another expanding universe that eventually began contracting, squeezed down to Planck scale densities, and then bounced to become our universe. Before that was another universe, and another, in an infinite chain of bounces stretching into the past and future. But here's a puzzle. If the universe has been bouncing forever, why does it look so young? The cosmic microwave background shows us a universe that's about 14 billion years old. Galaxies, stars, planets, all of it formed in the relatively recent past. If the universe has been through infinite cycles, shouldn't we see evidence of that vast history? The answer, according to loop quantum cosmology, is that each bounce essentially erases most information from the previous cycle. The extreme conditions at the bounce destroy complex structures. Galaxies are torn apart. Black holes evaporate. By the time the bounce is complete and the new expansion begins, the universe is filled with a hot, nearly uniform plasma, much like the early universe we observe. It's like shuffling a deck of cards. After enough shuffles, the original order is lost, and the deck looks random. Each cycle shuffles the universe, and by the time the next cycle begins, there's little trace of what came before. This raises the same entropy concerns as the other cyclic models. If entropy always increases, and the universe has been through infinite cycles, shouldn't we be at maximum entropy? Loop quantum cosmology doesn't have a clean answer to this. Some researchers argue that the bounce could somehow reduce entropy, or that the enormous expansion during each cycle dilutes entropy enough that the problem is avoided. Others admit that the entropy issue remains unresolved. But despite these challenges, loop quantum cosmology has some attractive features. It's based on a specific approach to quantizing gravity that, while not proven, is mathematically rigorous and well-developed. It makes predictions that could potentially be tested by observing the cosmic microwave background or primordial gravitational waves. And it provides a concrete mechanism for the bounce that doesn't require singularities or breakdowns in physics. Whether it's correct is another matter entirely. Loop quantum gravity itself is still controversial. It competes with string theory as a candidate theory of quantum gravity, and the two approaches are largely incompatible. Most physicists work on one or the other, and there's ongoing debate about which approach, if either, is on the right track. Speaking of string theory, there's yet another cyclic model we need to discuss. This one comes from Roger Penrose, one of the most brilliant and iconoclastic physicists alive. Penrose's idea, called conformal cyclic cosmology, or CCC, is both mathematically elegant and deeply weird. It starts with a question about the far future. Current observations suggest that the expansion of the universe is accelerating, driven by something called dark energy. If this continues, the universe will expand forever, becoming colder and emptier with each passing eon. Stars will burn out. Black holes will evaporate through Hawking radiation. Eventually, after perhaps 10 to the 100 years or more, the universe will consist of nothing but widely separated particles drifting through an expanding void. This is the heat death scenario, and it seems like the end of the story. But Penrose noticed something interesting. In this far future universe, there are no massive particles left. Everything with mass has either fallen into black holes which then evaporated, or has decayed into massless particles like photons. And in a universe containing only massless particles, something strange happens to the nature of time and space. Massless particles, like photons, don't experience time. From a photon's perspective, if we can call it that, it's emitted and absorbed in the same instant, regardless of how far it travels. The entire journey happens in zero time. In a universe containing only massless particles, time in a sense becomes meaningless. Penrose argues that in such a universe you can perform a mathematical transformation called a conformal rescaling. This is a change of coordinates that preserves angles but not distances. And after this rescaling, the infinite future of the old universe looks mathematically identical to the Big Bang of a new universe. The end of one aeon becomes the beginning of the next. The universe doesn't bounce in the traditional sense. It doesn't contract and then expand. Instead, through the properties of space-time geometry in the absence of massive particles, the infinite future smoothly transitions into a new beginning. It's as if time wraps around on itself, like a Mobius strip. You travel forward through time, reach what seems like an end, and find yourself at a new beginning. Now, this is an extraordinarily strange idea, and it requires some serious mental gymnastics to grasp. Penrose himself admits it's counterintuitive. But the mathematics, he argues, is sound. And, provocatively, he's claimed to find evidence for his theory in the cosmic microwave background. Penrose and collaborators have reported finding circular patterns in the CMB temperature maps that they interpret as the gravitational wave signatures of colliding black holes from the previous aeon. These collisions, they argue, left imprints that carried through the conformal transition and show up as rings in our CMB data. If true, this would be stunning. Direct observational evidence not just that the universe is cyclic, but that we can actually see traces of the previous cycle. However, most cosmologists are deeply skeptical. Multiple studies have analyzed the same CMB data and found that the patterns Penrose identified are consistent with random chance. When you have as much data as the CMB maps provide, you expect to see some patterns just by coincidence, like seeing shapes in clouds. The consensus is that Penrose hasn't proven his case, though he continues to defend his analysis. Even if the observational evidence isn't there, conformal cyclic cosmology remains an intriguing theoretical possibility. It offers a genuinely different way of thinking about cosmic cycles, one that doesn't require bounces or collisions but emerges from the geometry of space-time itself. But like the other cyclic models, it faces challenges. The entropy problem remains. If the universe has been through infinite aeons, each lasting hundreds of billions of years, why isn't entropy already at maximum? Penrose argues that the conformal transition somehow resets entropy, but many physicists find this unconvincing. There's also the question of whether the universe really will consist only of massless particles in the far future. If even a single massive particle survives, the conformal transition can't happen. And we don't know for certain that all massive particles will decay or disappear. What all these cyclic models have in common is a desire to avoid the idea of a true beginning. The notion that time itself started at a specific moment makes many physicists uncomfortable, perhaps because it raises questions about what came before, or what caused time to begin. If time is eternal, if the universe has been cycling forever, those questions dissolve. There's no beginning to explain, no first cause to seek. But eternal cycles come with their own baggage, especially the entropy problem. And none of the proposed mechanisms for resetting or avoiding entropy accumulation are entirely convincing. This is why inflation remains the dominant paradigm. It doesn't require eternal cycles. It doesn't require previous universes. It just requires a quantum fluctuation to get the ball rolling, and quantum fluctuations happen all the time. But inflation isn't perfect either, and some physicists remain skeptical. One of the most vocal critics has been Paul Steinhardt, who, ironically, was one of the early pioneers of inflationary theory. He's since turned against it, arguing that inflation is unfalsifiable because it predicts everything, and therefore predicts nothing. If inflation can produce universes with any properties, if eternal inflation generates infinite variations, how do we test the theory? What observation could possibly rule it out? These are fair criticisms, and they've sparked intense debate within the cosmology community. But most physicists still favor inflation because of its predictive successes and its ability to explain multiple puzzles with a single mechanism. The alternatives, while interesting, each have their own problems and lack inflation's broad explanatory power. There's one more alternative theory we need to discuss, and it's perhaps the strangest of all. This is the idea that our three-dimensional universe is embedded in a higher dimensional space, and the Big Bang resulted from our brain colliding with another brain. We touched on this with the ekpyrotic scenario, but there's more to the story. String theory, if correct, tells us that reality has more than 3 dimensions of space and 1 of time. Depending on which version of string theory you're working with, there could be 10, 11, or even more dimensions. We only perceive 3 spatial dimensions because the extra dimensions are curled up or compactified at scales too small for us to detect. But some versions of string theory suggest that not all extra dimensions need be tiny. 1 or more could be large, even infinite, and we simply can't access them because all the particles and forces we interact with are confined to our 3-dimensional brain. Imagine a sheet of paper floating in a 3-dimensional room. Creatures living on the paper's surface, truly 2-dimensional beings, would only be aware of the 2 dimensions of the sheet. They couldn't perceive the 3rd dimension of the room. If there were another sheet of paper nearby, parallel to theirs, they couldn't see it or interact with it directly. But if the sheets collided, they would definitely notice the effects. That's the brain collision scenario. Our universe is a 3-dimensional brain in a higher dimensional space called the bulk. There are other brains in the bulk, and occasionally they collide. When they do, the collision releases energy on the brains. Particles are created. Radiation floods the brains. From our perspective, confined to our brain, this looks like the Big Bang. One appealing aspect of this idea is that it explains why gravity is so much weaker than the other fundamental forces. Electromagnetism, the strong nuclear force, and the weak nuclear force are all confined to our brain. But gravity, in these models, can leak into the extra dimensions. Most of gravity's strength is diluted across the bulk, which is why it seems so weak compared to the other forces. This would also mean that at very short distances, where the extra dimensions become relevant, gravity could be much stronger than we expect. Particle accelerators might even create microscopic black holes if they reach high enough energies, though there's no evidence of this yet. Brain collisions could also explain dark matter and dark energy. Perhaps there are particles that live in the bulk rather than on our brain. They could still exert gravitational effects on our brain, which we would perceive as dark matter. unseen mass that affects galaxies and clusters. Or perhaps the expansion of the universe is driven by the motion of branes through the bulk, which could explain the accelerating expansion we attribute to dark energy. These are speculative ideas, but they demonstrate how brane cosmology opens up new possibilities for understanding mysteries in cosmology. The problem, as always, is testing these ideas. The extra dimensions, if they exist at large enough scales to be relevant for brane collisions, are still far too small for us to detect directly. We can't see other branes. We can't measure the bulk. All we can do is look for indirect signatures in the cosmic microwave background or in particle physics experiments. And so far, we haven't found definitive evidence for or against brane collisions. What we're left with is a menu of possibilities. Inflation suggests the Big Bang resulted from the decay of an inflaton field that might have started via quantum fluctuation. Cyclic models suggest the Big Bang was a bounce from a previous contracting universe, or a collision between branes. Loop quantum cosmology suggests quantum effects prevented a true singularity and caused a bounce. Conformal cyclic cosmology suggests the far future of a previous aeon transitioned into our Big Bang through geometric properties of spacetime. Each of these ideas has appealing features and troubling problems. Each makes predictions, though testing them is difficult with current technology. And each forces us to rethink basic assumptions about time, causation, and the nature of reality. What they have in common is an attempt to explain the Big Bang through natural processes, without invoking anything supernatural or fundamentally unknowable. The universe might have started from a quantum fluctuation. It might have emerged from a previous universe. It might be one of infinite universes in an eternally inflating multiverse. But in each case, it's explicable through physics, even if that physics is exotic and unfamiliar. This represents a profound shift in how we think about cosmic origins. For most of human history, the beginning of the universe was a religious or metaphysical question. Science couldn't touch it. But now we have mathematical models, observational evidence, and testable predictions. We might never know with certainty which model is correct. The ultimate beginning might remain forever beyond our reach. But the fact that we can ask these questions scientifically, that we can construct detailed models and compare them to observations, is itself remarkable. One thing that becomes clear when studying these alternatives to inflation is that they all face similar challenges. The entropy problem plagues every cyclic model. The origin of physical laws challenges every model that tries to explain the universe's beginning. The multiverse, if real, might make testing theories fundamentally difficult. And the Planck scale, that realm where quantum effects and gravity become equally important, remains beyond our experimental reach. We can't recreate Planck scale physics in laboratories. We can't observe it directly in the sky. We can only infer what might be happening based on mathematical extrapolations of theories that work at lower energies. This is both exciting and frustrating. Exciting because it means we're probing the absolute limits of physical reality, pushing our theories to their breaking points and discovering where they fail. Frustrating because without experimental guidance, we risk losing ourselves in mathematical speculation that has no connection to reality. String theory faces this criticism constantly. It's a beautiful mathematical framework, but after decades of work, it has yet to make a single testable prediction that distinguishes it from other theories. The same could be said of many of these alternative cosmological models. They're mathematically coherent, philosophically interesting, but not yet empirically confirmed. This is why the cosmic microwave background is so important. It's our window into the early universe, the one place where we can actually observe the conditions shortly after the Big Bang. The patterns in the CMB contain information about what happened during inflation or whatever process preceded the Big Bang. Future experiments will measure these patterns with ever greater precision, potentially distinguishing between different theoretical models. The same is true for primordial gravitational waves. If we can detect them and measure their properties, they'll tell us about the energy scale of inflation or whatever process generated them. Different models predict different gravitational wave signatures. Observation could rule some models out and support others. We're also learning more about the universe's large-scale structure. Surveys mapping billions of galaxies reveal patterns that reflect conditions in the very early universe. These patterns evolved from tiny quantum fluctuations, and the details of how they evolved depend on what happened in the first moments after the Big Bang. As our observations improve, our ability to test theories improves as well. But we need to be patient. The kinds of measurements required to distinguish between inflation, cyclic models, and other alternatives are extraordinarily difficult. They require satellites in space, telescopes at the South Pole, interferometers stretching across continents. They require decades of work by thousands of scientists. And even then, the answers might remain ambiguous. What's striking about all these alternatives is how strange they are. Branes colliding in higher dimensions. The universe bouncing through quantum effects. Time wrapping around on itself through conformal geometry. An infinite multiverse of bubble universes. These ideas sound like science fiction, and in a sense they are. But they're science fiction constrained by mathematics and guided by observations. They're not arbitrary fantasies, but serious attempts to make sense of the data and solve real problems. And that's what theoretical physics is all about. Taking what we observe, constructing mathematical models that explain those observations, and then following the mathematics wherever it leads, even if it leads somewhere strange. Sometimes the mathematics leads to predictions that seem absurd, but turn out to be true. Quantum mechanics predicted that particles could tunnel through barriers, which seemed impossible, but then we built scanning tunneling microscopes that use that effect. General relativity predicted black holes, which seemed like mathematical curiosities, but now we've photographed them and detected their mergers with gravitational wave observatories. So, maybe branes and bounces and cyclic cosmology seem strange now, but someday they'll be as accepted as black holes and quantum tunneling. Or maybe they'll be replaced by even stranger ideas we haven't thought of yet. The history of physics is full of theories that seemed outrageous when first proposed but eventually became orthodoxy. It's also full of beautiful theories that turned out to be wrong. We won't know which category these alternatives fall into until we have better data. And that might take decades or longer. In the meantime, we're left with a rich landscape of possibilities, each offering a different answer to the question of what started the Big Bang, and each revealing how much we still have to learn about the universe and our place in it. We've journeyed through the most ambitious theories physics has to offer, from quantum fluctuations to colliding branes, from eternal inflation to cyclic universes. We've seen how physicists have pushed the boundaries of knowledge back to the very edge of the Planck epoch, that first incomprehensibly brief moment when the universe was so small and dense that our theories break down completely. But now, we need to confront something uncomfortable. There might be a hard limit to what we can know, not because we lack clever theories or powerful telescopes, but because the universe itself might have permanently erased the evidence of its own beginning. This isn't just pessimism or defeatism. It's a serious possibility grounded in the physics of information and observation. Consider what happened in the very early universe. During the first few moments after the Big Bang, the universe was extraordinarily hot and dense. Particles collided with incredible energies. The fabric of space-time itself was wildly fluctuating. Any information about what came before, any clues about the initial conditions or the trigger that started everything, would have been thoroughly scrambled by these violent processes. It's like trying to reconstruct the original arrangement of ingredients in a cake after it's been baked, eaten, and digested. The information isn't just hidden, it's been transformed beyond recognition. Then there's the cosmic microwave background, our most important window into the early universe. This radiation shows us what the universe looked like about 380,000 years after the Big Bang. That might sound early, but it's an eternity compared to the Planck epoch at 10 to the negative 43 seconds. Everything that happened in those first moments left only the faintest of traces in the cosmic microwave background, and many details have been lost entirely. We can measure temperature fluctuations to extraordinary precision. We can detect patterns that tell us about inflation or whatever process preceded the hot Big Bang. But there's a limit to how much information the CMB contains. Once we've extracted every possible bit of data from it, once we've built telescopes sensitive enough to measure every subtle variation, we'll have learned everything the CMB can teach us. And there will still be questions it can't answer. The same is true for other observational windows. Primordial gravitational waves, if we detect them, will tell us about energy scales during inflation. The distribution of galaxies tells us about initial density fluctuations. The abundance of light elements tells us about nuclear reactions in the first few minutes. Each of these observations is like looking at the universe through a different colored filter. Each reveals some information while obscuring other details. And, crucially, all of them are observations of the universe long after the Planck epoch. We're seeing the universe after it had already expanded and cooled, after the initial conditions had already been set. We're seeing the consequences of whatever started the Big Bang, not the cause itself. This is why the Planck epoch represents such a formidable barrier. We can't observe it directly. Light couldn't travel freely until hundreds of thousands of years later. We can't recreate it in laboratories. The energies involved are too enormous. We can only extrapolate backward using our theories, and, as we've seen, our theories become increasingly speculative as we approach the Planck scale. We don't have a working theory of quantum gravity. String theory might be correct, or loop quantum gravity, or something we haven't thought of yet. Without experimental guidance, we can't know which approach is on the right track, and even if we had the correct theory of quantum gravity, it might not be enough. The theory could tell us what's possible, what kinds of initial conditions are allowed, what sorts of quantum fluctuations could occur. But it might not tell us why our particular universe, with its particular properties, came into existence. That might be a historical accident, a matter of chance rather than necessity. And if it's chance, then there's no deeper explanation to find. This is deeply unsatisfying to many physicists. Science is supposed to explain why things are the way they are, not just catalog possibilities. If the best answer we can give is quantum fluctuations happen with certain probabilities, and we got lucky, that feels incomplete. It feels like giving up. But it might be the truth. Not everything in the universe has a deeper explanation. Some things might just be brute facts, aspects of reality that simply are, without further justification. Consider the laws of physics themselves. Throughout this exploration, we've taken for granted that quantum mechanics works, that general relativity describes gravity, that the universe obeys certain mathematical principles. But why these laws and not others? Why does the universe follow elegant mathematical equations at all? Why is there something rather than nothing? These questions might be unanswerable, not because we're not smart enough, but because they're asking for explanations that can't exist. Every explanation must start with some assumptions, some foundation. If you try to explain the laws of physics, you have to use some other principles or framework, and then you can ask where those came from. It's turtles all the way down. At some point, you have to stop and accept that certain things are fundamental, that they don't have further explanations. Different physicists draw this line in different places. Some are comfortable saying the laws of quantum mechanics are fundamental and don't require further explanation. Others want to derive those laws from even deeper principles. But everyone eventually has to stop somewhere. And wherever you stop, you're left with the question, why this foundation and not another? The anthropic principle, controversial as it is, offers one way out of this infinite regress. If there are infinite universes with different laws, then we don't need to explain why the laws of physics are what they are in our universe. They just happen to be the ones compatible with our existence. In universes with different laws, different questions would be asked by different kinds of observers, if observers could exist at all. But this shifts the mystery rather than solving it. Now we have to explain why the multiverse exists, why there's a mechanism for generating universes with different properties. And we're back to the same problem. Unless the multiverse itself is fundamental, unless it's just a brute fact that needs no further explanation, we haven't really made progress. We've just moved the unexplainable thing one level up. Some philosophers argue that this is inevitable. There has to be something that's fundamental, that exists without explanation. Whether it's God, or the laws of physics, or the quantum vacuum, or the multiverse, something has to be the bedrock of reality. The scientific approach is to push that bedrock as deep as possible, to explain as much as we can before we hit the limits of explanation. And we've pushed it remarkably deep. We've explained the formation of galaxies, the synthesis of elements, the expansion of space, the evolution of stars, the origin of planetary systems. We've traced the universe's history back to a fraction of a second after the Big Bang. We've developed theories that potentially explain even that first fraction of a second. But the ultimate origin, the question of why there's a universe at all, might remain forever beyond reach. This isn't a failure of science. It's a recognition of what science can and can't do. Science explains how things work, how they change, how they relate to each other. It's extraordinarily good at answering how questions. But why questions, especially ultimate why questions, might not be scientific questions at all. Let's look at what we're actually doing when we search for the origin of the Big Bang. We're trying to find earlier causes for later effects. Inflation explains the hot Big Bang. Quantum fluctuations explain inflation. But what explains quantum fluctuations? Perhaps the laws of quantum mechanics do. But what explains those laws? At each step, we're reducing the mystery, explaining one phenomenon in terms of more fundamental phenomena. But this process has to terminate somewhere. Either we reach truly fundamental phenomena that have no further explanation, Or we discover that the chain of explanation is circular, with each thing ultimately explaining itself through a loop of causation. Neither option is fully satisfying, but one of them must be true. A third possibility is that the question itself is malformed. Perhaps asking what started the Big Bang is like asking what's north of the North Pole. The question assumes something, a direction called north, that doesn't exist at the pole. Similarly, asking what started the Big Bang assumes something, time before the Big Bang, that might not exist. If time itself began with the Big Bang, or emerged from some timeless quantum state, then what started it is asking for a cause that preceded an effect in time. But if there's no time before the Big Bang, there's no before in which a cause could operate. This is the kind of conceptual knot that philosophers and physicists have been wrestling with for decades. It's not clear that we have the right conceptual framework to even pose the question properly, let alone answer it. Stephen Hawking, in his later years, seemed to embrace this view. He argued that asking what came before the Big Bang was meaningless because time didn't exist before the Big Bang. It's not that something existed before and we can't know what it was. It's that before itself doesn't apply. The Big Bang wasn't an event that happened at a moment in time. It was the beginning of time. This is a coherent position, but it's also deeply counterintuitive. Our entire experience of reality involves time flowing from past to future. Every event we've ever witnessed had prior causes. The idea that this chain of causation simply stops at the Big Bang, that there's no earlier cause to find, goes against every instinct we have. And yet, it might be true. Or it might not. The honest answer is that we don't know. We have multiple competing theories, each with its own strengths and weaknesses. We have observations that constrain those theories, but don't definitively prove any of them. And we have fundamental limits on what we can observe and test. So, where does that leave us? Are we stuck forever in ignorance about the universe's ultimate origin? Not necessarily. Science has a way of surprising us. Technology advances. New theoretical insights emerge. Observations that seemed impossible become routine. Consider gravitational waves. For decades, they were a theoretical prediction of general relativity with no hope of direct detection. The signals were too weak, the technology too primitive. Many physicists doubted they'd ever be observed. Then, in 2015, LIGO detected gravitational waves from colliding black holes, opening an entirely new window onto the universe. Within a few years, gravitational wave astronomy had become a thriving field. The same could happen with our questions about the Big Bang. Maybe future experiments will detect primordial gravitational waves that reveal the energy scale of inflation. Maybe advances in quantum gravity will allow us to calculate what kinds of quantum fluctuations are possible and how likely each one is. Maybe we'll find indirect evidence for the multiverse by detecting patterns in the cosmic microwave background that only make sense if our universe is one bubble among many. Or maybe the breakthrough will come from an unexpected direction. Maybe studies of black hole interiors will reveal something about the Planck epoch, since both involve extreme curvature and quantum effects. Maybe particle accelerator experiments will discover new physics that changes our understanding of the early universe. Maybe a brilliant theorist will have an insight that reframes the entire question in a way that makes the answer obvious. This has happened before in physics. Problems that seemed intractable for generations suddenly became solvable when someone looked at them from a new angle. Maxwell's equations unified electricity and magnetism in a way that seemed impossible before. Einstein's relativity resolved paradoxes that had plagued physics for years. Quantum mechanics explained atomic structure that classical physics couldn't touch. Each of these breakthroughs required not just new data, but new ways of thinking. And there's no reason to believe we've exhausted the possible ways of thinking about cosmic origins. That said, we also need to be realistic. Some questions might genuinely be unanswerable. The universe isn't obligated to be comprehensible to human minds. We evolved to survive on the African savanna, to track animals and gather plants and navigate social relationships. The fact that our brains are capable of understanding relativity and quantum mechanics at all is somewhat miraculous. But there might be aspects of reality that are simply beyond our cognitive capacity, like trying to teach calculus to a dog. The dog's brain isn't wired for abstract mathematics, and no amount of training will change that. Similarly, our brains might not be wired to understand certain features of reality. We might be asking questions that are in principle answerable, but that we'll never be able to grasp because we lack the necessary mental hardware. This is a humbling thought, but it's worth considering. It's possible that the deepest truths about the universe will remain forever beyond human comprehension. But even if that's true, it doesn't mean we should stop trying. Every bit of understanding we gain is valuable, even if complete understanding is impossible. And the process of trying to understand, the act of pushing against the limits of knowledge, is worthwhile in itself. Let's talk about what we're learning right now. What experiments and observations are underway that might shed light on these questions? The cosmic microwave background continues to be studied with ever greater precision. Satellites like Planck have mapped temperature fluctuations to incredible accuracy. Ground-based telescopes in Antarctica are measuring polarization patterns. These observations are testing inflationary predictions and looking for signs of primordial gravitational waves. If those gravitational waves are detected, they'll tell us about the energy scale during inflation, which will constrain theoretical models significantly. The James Webb Space Telescope is observing the earliest galaxies, those that formed just a few 100 million years after the Big Bang. By studying how these first galaxies assembled, we learn about the initial density fluctuations that seeded their formation. Those density fluctuations originated from quantum effects during inflation or whatever process preceded the hot Big Bang. So, observations of the first galaxies are, in a sense, observations of quantum processes in the very early universe. Particle accelerators like the Large Hadron Collider are recreating conditions from microseconds after the Big Bang. By studying what happens at these enormous energies, physicists learn about the particles and forces that dominated the early universe. While we can't reach Planck scale energies, we can get close enough to test aspects of theories like supersymmetry or extra dimensions, which are relevant to models of cosmic inflation and quantum gravity. Gravitational wave observatories are also improving. LIGO and Virgo have been detecting black hole and neutron star mergers for several years now. Future detectors like LISA, a space-based gravitational wave observatory, will be sensitive to lower frequencies and might detect signals from the very early universe. If cosmic strings exist, remnants from phase transitions in the early universe, they would produce distinctive gravitational wave signatures. Detecting them would be direct evidence for specific models of the Big Bang's origin. There are also more speculative ideas for future observations. Some physicists have proposed looking for collision signatures in the cosmic microwave background, evidence that our bubble universe collided with another bubble in the eternal inflation picture. Others suggest looking for patterns that might indicate our universe is a simulation, though this veers more into philosophy than testable science. The point is that observational cosmology is a vibrant, active field. New data is coming in constantly, and while it might not directly answer the question of what started the Big Bang, it narrows down the possibilities and tests the predictions of different theoretical frameworks. This is how science makes progress. Not usually through single dramatic breakthroughs, but through gradual accumulation of evidence that favors some theories over others. On the theoretical side, work continues on quantum gravity. String theorists are exploring how their framework describes the universe's earliest moments. Loop quantum gravity researchers are calculating what happens at the Planck scale in their models. Other approaches, like causal set theory or emergent gravity, offer different perspectives. None of these approaches has achieved the status of confirmed theory. They're all works in progress, mathematical frameworks that might or might not describe reality. But each pushes our understanding forward, revealing new possibilities and constraints. Even if string theory turns out to be wrong, the decades of work on it have taught us enormous amounts about quantum field theory, black hole physics, and the mathematics of extra dimensions. That knowledge will inform whatever theory eventually succeeds. This is why theoretical work is valuable, even when it doesn't immediately lead to experimental confirmation. It expands the space of possibilities, shows us what kinds of explanations are mathematically consistent, and prepares us for whatever future observations reveal. When LIGO detected gravitational waves, physicists were ready with detailed predictions about what the signals should look like. Decades of theoretical work on general relativity had prepared them. Similarly, when we finally get definitive data about the Planck epoch, however that happens, decades of work on quantum gravity will prepare us to interpret it. But let's be honest about the challenges. The energies involved at the Planck scale are so enormous, the distance is so small, that direct observation seems impossible. Building a particle accelerator powerful enough to probe Planck scale physics would require a machine the size of the Milky Way galaxy. That's not an exaggeration. The energy needed is about 10 to the 19 times greater than what the Large Hadron Collider can achieve. We're not building a galaxy-sized particle accelerator anytime soon. We have to rely on indirect observations, on relics from the early universe like the cosmic microwave background or primordial gravitational waves. And those observations, while incredibly valuable, can only tell us so much. There's information that's been irretrievably lost to entropy and expansion. We're like archaeologists trying to reconstruct an ancient civilization from a handful of artifacts. We can learn a lot, but there are limits to how detailed our reconstruction can be. This is why some physicists have suggested that the question of the Big Bang's origin might be one that science can't fully answer. Not because the question is unscientific, but because the evidence we need has been destroyed by the universe's own evolution. There's also the possibility that the answer, even if we found it, would be unsatisfying. Suppose we definitively proved that the universe arose from a quantum fluctuation in the vacuum. We'd still be left asking why the vacuum has the properties it does, why quantum mechanics works the way it does, why fluctuations are possible at all. We'd have explained one mystery in terms of another mystery. This is sometimes called the problem of infinite regress. Every explanation raises new questions, and at some point, We have to either accept that certain things are fundamental and need no further explanation, or admit that explanation has limits. Different people draw this line in different places based on their philosophical preferences. But everyone has to draw it somewhere. The beauty of the scientific approach is that it keeps pushing the line back, explaining more and more in terms of less and less. Newton explained falling apples and orbiting planets using the same law of gravity. Maxwell explained electricity, magnetism, and light as different aspects of electromagnetism. Einstein explained gravity as space-time curvature. The Standard Model explains hundreds of particles in terms of a few fundamental fields. This process of unification, of finding common explanations for seemingly disparate phenomena, is one of science's greatest triumphs. And we're continuing that process with theories of cosmic origins. We're trying to explain the Big Bang, the universe's properties, and the existence of structure all in terms of deeper principles. But there might be a point where this process ends, where we reach principles that are truly fundamental and can't be reduced further. We might be close to that point already. The laws of quantum mechanics and general relativity are extraordinarily fundamental. It's not clear what more basic principles could underlie them. Of course, physicists have been wrong about reaching fundamental principles before. In the 19th century, some thought physics was nearly complete. Then, relativity and quantum mechanics revolutionized everything. So, we should be cautious about claiming we're near the end of the road. But it's at least possible that the question of what started the Big Bang is close to the limits of what physics can explain. Not because physicists aren't clever enough, but because we've reached something genuinely fundamental that doesn't have a deeper explanation. If that's the case, then the answer to what started the Big Bang might be quantum fluctuations in the vacuum, or a collision between branes, or the universe's wave function being in a particular state. And if we ask why the vacuum fluctuates, or why branes collide, or why the wave function has that form, the answer might simply be, that's how reality is. This doesn't mean the question was silly or that studying it was pointless. We've learned enormous amounts by pursuing these questions. We've developed sophisticated theories, made detailed predictions, and tested many of them with observations. We've pushed our understanding to the absolute limits of space and time. That's an achievement worth celebrating, even if some mysteries remain. There's also something profound about the fact that we're asking these questions at all. Think about what has to be true for beings like us to exist and ponder the universe's origin. The Big Bang had to happen. Inflation or something like it had to smooth out the universe and generate density fluctuations. Those fluctuations had to grow under gravity to form galaxies. Stars had to form from collapsing gas clouds. Nuclear fusion in those stars had to produce carbon, oxygen, nitrogen, and other heavy elements. Those stars had to explode as supernovae, scattering their enriched material into space. New stars and planets had to form from that enriched material. On at least one planet, chemistry had to become complex enough to produce self-replicating molecules. Those molecules had to evolve over billions of years into increasingly complex life forms. Eventually, some of those life forms had to develop brains capable of abstract reasoning, language, mathematics, and science. All of this had to happen for us to be here, asking what started the Big Bang. We are, quite literally, the universe becoming conscious of itself. We're made of atoms forged in stellar furnaces, assembled by chance into forms capable of contemplating existence. The fact that this is possible at all is remarkable. The fact that we can trace our origins back to the first moments of the universe is astonishing. And the fact that we can ask scientific questions about those first moments, that we can construct mathematical models and test them with observations, is a triumph of intelligence and curiosity. So, even if we never fully answer the question of what started the Big Bang, even if some aspects of cosmic origins remain forever mysterious, we've still accomplished something extraordinary. We've shown that questions about the universe's beginning aren't beyond the reach of science. They're difficult questions, perhaps the most difficult questions we can ask, but they're approachable through observation, mathematics, and logical reasoning. That's a profound shift from just a century ago, when questions about cosmic origins were purely philosophical or theological. We've brought them into the realm of science, and in doing so, we've expanded the scope of what science can address. Looking forward, what can we expect? In the next few decades, observations will continue to improve. The cosmic microwave background will be mapped with greater precision. Gravitational wave detectors will become more sensitive. New telescopes will observe ever earlier epochs of cosmic history. Each of these observations will test our theories and potentially rule out some possibilities. We might get lucky and find a smoking gun, a definitive signature that tells us exactly what happened in the first moments after the Big Bang. Or we might find that all our current theories are wrong, that nature has surprises we didn't anticipate. That would be exciting too, in its own way. It would mean we have more to learn, that the universe is even stranger than we thought. On the theoretical side, work on quantum gravity will continue. String theory, loop quantum gravity, and other approaches will be developed further. Perhaps one of them will make a prediction that's testable with current or near-future technology. Perhaps they'll converge, revealing that they are different mathematical descriptions of the same underlying reality. Or perhaps an entirely new approach will emerge that makes the others obsolete. We can't predict which of these scenarios will unfold. That's part of what makes science exciting. We're exploring unknown territory, and we don't know what we'll find. But we keep exploring because the alternative, accepting ignorance without trying to understand, is unacceptable. Humans are curious by nature. We want to know how things work, where we came from, what our place is in the cosmos. These aren't idle questions. They're fundamental to how we understand ourselves and our relationship to reality. And so we'll keep asking them. Keep probing deeper. Keep pushing the boundaries of knowledge. Even if the ultimate answer remains beyond our reach, the journey is worthwhile. Every step forward, every mystery solved, every question answered, enriches our understanding and opens new avenues for exploration. The question of what started the Big Bang might be the deepest question we can ask. It probes the very nature of existence, time, causation, and reality itself. Different answers lead to radically different worldviews. If the universe arose from a quantum fluctuation, it suggests that existence itself might be a cosmic accident, needing no deeper justification. If it emerged from a previous universe in an eternal cycle, it suggests that existence has no beginning, that the chain of cause and effect extends infinitely into the past. If it was created by some external agency, whether you call that God or a programmer or something else, it suggests that our universe is contingent, dependent on something beyond itself. Science alone can't definitively choose between these possibilities. At some point, we cross from physics into metaphysics, from what we can observe and test to what we can only speculate about. But science can narrow down the possibilities, can show which scenarios are consistent with observations and which aren't. It can push the boundary between the known and unknown further back, even if it can't eliminate the unknown entirely. And that's enough. That's what science does. It doesn't claim to answer every question or solve every mystery. It claims to be the best method we have for understanding the natural world, for distinguishing truth from falsehood, for building reliable knowledge about reality. And by that standard, our investigation of the Big Bang's origin is a spectacular success. We've traced the universe's history back nearly to its beginning. We've developed theories that explain what happened in the first fraction of a second. We've made predictions that have been confirmed by observations. We've shown that the universe's origin, mysterious as it is, isn't beyond the scope of scientific inquiry. That's a remarkable achievement. Our ancestors looked at the night sky and told stories about how the universe began. Those stories were beautiful and meaningful, but they weren't scientific. They didn't make testable predictions. They didn't constrain what we might observe. We've gone beyond stories. We have equations that describe the universe's expansion. We have observations that map the cosmic microwave background. We have theories that connect quantum mechanics to cosmology. We're doing science at the absolute frontier, grappling with questions at the edge of what's knowable. And in that struggle, in that relentless push to understand, we're doing something fundamentally human. We're refusing to accept easy answers. We're demanding evidence and logical reasoning. We're subjecting our ideas to brutal scrutiny and discarding those that fail the test. This is how science works. It's difficult, often frustrating, and never final. Every answer raises new questions. Every theory eventually gets replaced by a better one. But progress is real. Our understanding deepens over time. And the questions we're asking today would have seemed like magic or divine knowledge to our ancestors. So, where are we in understanding what started the Big Bang? We're further along than you might think, given how mysterious the question seems. We have plausible mechanisms, from quantum fluctuations to cyclic bounces to brane collisions. We have observations that test these mechanisms. We have ongoing experiments that will provide more data in the coming years. But we're also realistic about the limits. Some information might be irretrievably lost. Some questions might be unanswerable in principle. And the ultimate why, the reason existence itself is possible, might be beyond the scope of physics entirely. That's okay. Science has never claimed omniscience. It's a method for gaining reliable knowledge about the natural world, and it's extraordinarily good at that. But it's not the only way humans make meaning or seek understanding. Philosophy, art, religion, personal experience, all of these contribute to how we make sense of reality. Science gives us one kind of answer to the question of cosmic origins, an answer based on observation and mathematics. Other disciplines give other kinds of answers, based on different values and methods. All of them are part of the human response to the mystery of existence. And existence is mysterious. The fact that there's something rather than nothing, that the universe exists and we exist within it, that we're capable of asking these questions at all. That's genuinely puzzling. It might be the ultimate puzzle, one that can't be fully solved because any solution would itself require explanation. But even if we can't reach the absolute bottom, we can go deeper than we are now. We can keep learning, keep observing, keep theorizing. We can push the boundaries of knowledge further with each generation. And in doing that, in that continuous quest for understanding, we honor what's best about being human, our curiosity, our intelligence, our refusal to be satisfied with ignorance. 13.8 billion years ago, something happened. We call it the Big Bang. We don't fully understand what started it. We might never fully understand. But we're asking the question, and we're making progress, and that matters. Because in asking how the universe began, we're really asking how we began. We're seeking to understand our place in the cosmos, our connection to the grand sweep of cosmic history. And in that seeking, in that reaching toward ultimate questions, we're participating in something larger than ourselves. We're part of the universe's long journey from simplicity to complexity, from unconscious matter to conscious minds capable of wonder. That journey started with the Big Bang, and it continues in every question we ask, every observation we make, every theory we construct. We are the Big Bang's legacy, its children, carrying forward the process of cosmic evolution into the realm of thought and understanding. And in that sense, asking what started the Big Bang isn't separate from us. It's part of who we are, what we do, why we matter. The question itself is an answer, or at least part of one. We exist. We wonder. We seek. And in doing so, we give meaning to the cosmic story, adding a new chapter written in curiosity and awe.